My name is Dr Michelle Dickinson. I've learnt that breaking things down is the easiest way to understand them. So join me. We'll break down scientific concepts, meet some amazing scientists and inventors, and help you discover the world around you.
Hi, I'm Dr Michelle Dickinson, and today we're going to be talking about energy. When most people talk about energy, they're normally talking about how they feel, like whether they're low in energy and feel tired, or whether they're super energized and ready for action. Scientifically though, the word energy is actually defined as the ability to do work, and energy makes things happen. It's needed for things to change and for things to move. Today, we're going to look at how harnessing energy makes our everyday lives possible. We're going to look at different types of energy, how we can generate electricity, and alternative ways of powering our world. To join in with our energy experiments, you will need an elastic band, a little bit of card, a sheet of paper, a blob of blue tack or plasticine, a pencil, some tape, and a plastic ruler. And of course, don't forget your notebook and pen so you can write down your observations. If you haven't got those things to hand, go grab them now. A bit later, I'll be calling one of my science helpers who'll be joining us from home and speaking to one of my friends who'll be able to tell us even more about harnessing and converting energy. Let's get started. Let's look closer at what we mean by energy. Energy is everywhere, and it comes in lots of different forms. Heat, light, sound, and movement are all different types of energy. Energy makes any action possible, whether that's driving to school, raising your hand in class, or running for the bus. Something to get your head around is that energy cannot be created or destroyed. It can only be changed into different forms. An example, let's think about your breakfast. Whether it was cereal or toast, it would have contained chemical energy that your body will have then converted to potential energy, which it will store. Then, when you went to grab the things you needed for today's experiments, you converted that stored potential energy into kinetic energy as you got up and moved around. So actually, you've already done your first experiment today. Again, think about the fact that energy cannot be created or destroyed. It can only be changed into different forms. And let's take a moment to think about different ways that you have seen energy changed from one form to another. Okay, one of the forms of energy that has changed our lives is the energy that we call electricity. And electricity typically comes from a power plant. Traditionally, power plants produce electricity by changing the chemical energy in a fuel, such as coal, into electrical energy. First, the coal is burnt, converting its chemical energy into heat energy. Next, the heat turns water into steam, and this moves a turbine motor or generator. Finally, the movement of this generator produces electricity. To understand electricity more, we first need to understand atoms. Everything in the universe, the sun, grass, dirt, even us as people, are made of atoms. And atoms are tiny things, way too small for us to see with just our eyes. They're referred to as the building blocks of everything. Even though they are super tiny, atoms themselves are made up of even smaller building blocks. We call these protons, neutrons, and electrons. The protons and neutrons stay clumped together in the center of what's called a nucleus, and the electrons spin around this center. Electrons are negatively charged, and they stay in orbit because they are attracted to the positively charged protons in the nucleus. You may have heard the saying, opposites attract. Well, this is very much true when it comes to atoms. To create electricity, electrons need to be able to move between atoms. in a way that causes a net flow of electrons in one direction. When outside forces, such as friction or chemical reactions, shift or polarize the balance of positive and negative charges, we can get this flow of electrons. The electrons keep moving across the conductive material in a similar way to how water flows. The electricity that powers our homes is from the flow of electrons. This is the type of energy that flows through conductive wires in our homes and powers our lights, televisions, computers, and all of our appliances. Our power sockets in the wall work by stopping and starting this flow of electricity. When electrons aren't flowing freely because their material is not conductive, they can instead build up on a surface. And once they are able to release this buildup by being in contact with something conductive, they all shoot towards that surface. You might have experienced static electricity if you've ever been zapped by a car door. But have you noticed that this happens more in the winter? That's because the air tends to be drier and you tend to be wearing more layers of clothing. As you move about, the fabric on your clothing rubs together. And this rubbing action creates a transfer of electrons, which build up until they can release themselves by finding another conductive material to jump to. When they jump, you get zapped. Okay, now we understand energy conversion and electricity. It's time for a couple of experiments. Let's check in with my science helper to see if they're ready to go. Hey Hudson, how are you?
Good, how are you?
I'm great. Thank you for helping me do a science experiment today. Just checking you've got everything you need in front of you. So you should have some sticky tape, some paper, blue tack or plasticine, card, a rubber band, a pencil, and a plastic ruler.
Yes, I have all those.
Now, have you ever made a paper plane before?
Yes.
Have you ever made a catapult before?
No.
Well, we're going to combine those two and we're going to make a catapult plane. Have you made one of those?
No, I've never made one of those.
Because we're talking about energy today and we're going to show you how you can actually convert potential energy into kinetic energy, which is stored energy into something that moves. So here's what you need to do. You should have a little sheet of paper that's about 16 centimeters by 8 centimeters.
Yes, I do.
I want you to fold it in half lengthways for me.
Yep.
Perfect. And then fold it again in that same direction lengthways. So you're going to end up with a long, thin rectangle.
Yep.
Awesome. Now take your rubber band and I want you to hold it about 1 centimeter in from the top.
Yep.
And then fold the top over so it's become a hook that holds the elastic band in there. And you're going to tape the end of the paper down so it holds onto the elastic band.
Okay, there we go.
Perfect. Now this is going to be your firing mechanism. So the elastic band here is going to store your potential energy as you stretch it and hopefully let your catapult fire. Now the next thing we need to do is attach this to your plane. So you should have a triangle of card. This is about 12 centimeters by 12 centimeters. You can make it out of cereal box card. And what I want you to do is line up your top of your triangle and the end of your rectangle that's got the rubber band on it, because this is going to be where it fires from. And then you're just going to tape the two together. Make sure you don't tape the rubber band.
There we go.
Perfect. So you should have a rubber band on the top of your card, and on the inside you have a flappy, secured piece of paper. Now, for this to fly well, it's going to need a little bit of weight on the front. You can either add a paper clip, or I've got some blue tack. Have you got something to weight down the front?
Yep.
Squish it down, and it's going to give your plane a bit of weight so that it will fly a little bit better.
Cool.
Okay, now it's time to fire it. So if this works, we're going to turn potential energy into kinetic energy. So we're going to hold the tail with one hand and then put the elastic band at the top of your thumb on the other hand. Don't point it at people. Now, as you stretch out the elastic band, that's going to store all this potential energy. And then when you let go, it should turn to kinetic energy.
Whoa.
It flies pretty well, right?
Yeah.
So that is a really easy way to show how we can convert energy from one form to the other. Now, next experiment is all about something called static electricity. Have you ever had a static shock before?
Yes, from a balloon.
Now, did it feel like it zapped you?
Yeah, and it was this weird little tingle thing.
So we're going to create static electricity, but we're not going to shock you today, okay? We're going to use it instead to move something. So I want you to take your blob of blue tack or plasticine, put it on the table, and then put your pencil inside. So it stands upright with the point pointing up. Next, you should have a little rectangle of paper. Mine's about 9 centimeters by 4 centimeters. I want you to fold it in half one way.
Yep.
And then unfold it, and then fold it in half the other way. So you're going to create a cross out of creases.
Yep.
So you should be able to see where the middle is of your rectangle now.
Yep.
And you're going to squeeze together the ends a bit so that middle becomes very clear, and you want to balance that on top of your pencil. Perfect.
Good.
Okay. You should have a plastic ruler in front of you, and we're going to negatively charge that, and we're going to do that by rubbing it on our heads. So rub on your head. What you're doing is creating a negative charge on your ruler. Now, we know that opposites attract, but we also know that like charges don't like each other and they repel, and we're going to use that. So I want you to put your ruler close to your sheet of paper and see what happens.
Whoa. It's moving. That's so cool.
And so what you're doing there is you're using the negative charge from your ruler, and it's getting to the negative charge in the paper, and we know that like charges repel, so that the negative charges in the paper are trying to get away from your ruler, and that has enough force to actually be able to move it away and rotate your paper there. So that is an easy way that you can trick people and say, how do you get this paper to move without touching or blowing on it? And actually, it's using static electricity. Thank you for helping me, Hudson. I will see you next time.
Bye.
Okay, after any experiment, we need to write down our observations. These help us to understand our results and make interesting predictions for our next experiments. So, today, what did we observe? We saw that the elastic band was able to store potential energy when we stretched it, and this potential energy converted to moving kinetic energy when we let it go. We also saw that the buildup of charge on the ruler was enough to push away its like charges on the paper. We know that opposites attract, but today we saw that like charges repel. Now let's look at our observations and reflect on them. By asking questions about why something happened or how we might make it happen again, we're really starting to understand the science behind it. For example, we saw what happened with the elastic band and the static ruler. Do you think the catapult plane would fly as well if the elastic band was really cold or really warm? Why do you think a plastic ruler was used today instead of a metal one or maybe a wooden one? Do you think the experiment would still work if we used a different material? So we've learned about different forms of energy, we've learned about electricity, but where does our energy come from? On Earth, we have one main energy source, and that is the sun. Nearly all of our energy comes to us ultimately from the sun. We know it makes our plants grow, it can help us to grow, and as a planet, we actually need the sun to survive. In terms of electricity, the sun gives us solar power. However, at the moment, we haven't worked out a way to harness this solar power very efficiently. If we could, we would have an abundance of renewable power. My guest today is Professor Justin Hodgkiss, and he is working on exactly how we could solve that problem. Justin Hodgkiss is co-director of the MacDiarmid Institute and works in the field of physical chemistry. He is developing low-cost solar panels to best make use of the sun's energy, helping to bring us closer to a sustainable future. Hi Justin, how are you?
Hi Michelle, very good, thank you.
Can you just introduce yourself, please?
My name's Justin Hodgkiss. I'm a professor of chemistry at Victoria University Wellington, and I'm also co-director of the MacDiarmid Institute.
Did you like science when you were a student?
I think probably it wasn't until towards the end of my university studies that I really thought that I would become a scientist. But I certainly, as a child, I liked building things, breaking things, figuring out how things work. I liked solving puzzles, And that's really what science is.
Now, obviously you love your job. What do you think the coolest thing is about your job?
The chance to really make a big difference. That's the thing that drives me. And my research is about trying to discover new materials for solar cells, and clearly that could have a massive impact to mitigate climate change.
You've mentioned solar cells, but what exactly are you doing?
So we're trying to discover new classes of solar cells that can be low cost because they can be printed, and they're actually made out of plastic essentially. So the existing solar cells that you see today on rooftops, they're made of a semiconductor called silicon, but on a rooftop it's on a pane of glass, so it's solid and it's heavy. And it's more expensive than we would like. I mean, the reason that they're not everywhere is because not everybody can afford to put them everywhere. So we're making things that are very lightweight, low cost, can just be printed roll to roll. And what we get to do in my lab is shoot laser beams at them and figure out how light is converted into electricity and how we can design materials to do that more efficiently.
So shooting laser beams at things is a theme that we seem to like on this show, and I'm excited to learn more about your lab. So what else do you have in your lab other than laser beams?
Laser beams, even cooler than that. So the laser beams that we have pulses that are femtoseconds long. And so a femtosecond is a millionth of a billionth of a second. So that's 10 to the minus 15 seconds. And to put that into some other kind of context for you, a femtosecond is to a second as a minute is to the age of the universe, roughly. So these are really, really, really short. Why do we need them that short? It's because we're kind of doing strobe photography, if you like, with these really short flashes of light. We're kind of doing strobe photography of what happens to electrons in the material.
I'm already excited about your research, but what do you enjoy most about your job?
Being thrust into the unknown. Things that we just don't understand. It's all just a big puzzle, and we're solving it together as a team. With my PhD students, where we get some measurements that we don't understand. We're trying to figure it out, and we know that if we do figure it out, it could actually make a real difference in the world. If we're able to contribute to the understanding of new solar cell materials that will one day reduce carbon emissions and be affordable for everyone, then it doesn't need much more motivation than that to solve the problem.
I totally agree with you. And you know what? I'm really jealous that I can't visit you right now because femtosecond lasers sound awesome. And it looks like they're going to help us produce the energy of the future, at least through different types of solar cells. Justin, thank you so much for your time today. We're going to go keep learning more about energy and electricity.
Thank you.
Historically, burning coal or fossil fuels was the main way that we produced electricity. Now we know that fossil fuels are not great. One, because they might run out, and two, because when we burn them, they can create chemicals that can be harmful to our environment. These days, we're focused on finding renewable sources of energy, often referred to as clean energy. Clean energy comes from natural sources or processes that are constantly replenished. This means that it doesn't run out, and you don't have to burn anything to get it. Therefore, there are no harmful chemicals produced. There are several different areas that we look at for clean energy. For example, the wind, the sun, and water. By the way, did you know that the sun's rays produce more energy in 1 hour than is used by everybody in the world in 1 year? However, at the moment, most success that we're having is with wind. Have you ever wondered where wind actually comes from? It's produced because the sun heats the Earth's surface unevenly. Some parts of the Earth get really hot, whereas others don't. Now we know that hot air rises, so in the hot places, the air rises and the cold air moves in underneath to replace it. This sets up what we call a convection current, a cycle of rising and then sinking air, which is how wind currents start. Wind turbines are built in places where they can catch the wind almost every day. These giant structures with their huge blades turn using the force of the wind, which then turns a rotor inside them, providing kinetic energy. This kinetic energy then powers a generator, which produces electricity. Another big producer of energy is water. We call this hydropower, and it relies on fast-moving water, such as from a dam or in a large river. And it converts the force of this flowing water into electricity through a water turbine. All over the world, a huge amount of human energy is being poured into finding more efficient ways of harnessing renewable energy. If you've ever been in a power cut, it becomes very clear just how much electricity we rely on to keep our whole lives going. This is such an exciting area of research, because now not only are we creating new technologies, we're also helping to solve some big problems like environmental damage as well as climate change. Hopefully, now you have an understanding of energy and what role electricity plays in that. Put simply, without energy, everything would just stop. I never get tired, ironically, of thinking about how energy continues to change form again and again and again. It's crazy to think that it can't run out and that it's just moved on to becoming something different. Saying that, it's still really annoying when the battery goes flat in our phones. Don't forget to keep questioning your world around you too. It's these questions that you ask every day that make for new discoveries tomorrow. Teachers and parents, don't forget to visit nanogirlslab.com, where we have downloadable content to help you continue on your science journey of electricity and energy. Will solar power work on cloudy days? Can waves in the ocean be used to turn a turbine? How much of New Zealand's energy is provided by renewable sources? How do clouds make lightning? If you were to build a wind farm in your neighborhood,